And this is our official start of data structures for today. I hope you all had a great spring break, very restful. And I'm glad those of you not in the Claremont time zone got the figured out about time changes and how that all affects you and were able to connect up with us. The first thing, before talking about actual material for today, I want to just talk a little bit more about time zones and time and computer science and how that affects us. I'm going to share my screen real quick. And here I've just pulled up this, an issue that I opened up today. And there's these 3 links at the bottom to 3 short videos. They're not required watching for the class. You're not going to be tested on them at all, but I do definitely recommend them because they have some like really fascinating material. And sort of the short of it is that time is really, really complicated in computer science. So dealing with time zones, for example, in the US, we have like daylight savings time. And so twice a year, we have to think about adjusting our clocks. But there are other countries in the world that have even like significantly more complicated time zones than the US. So as an example, there are some time zones that rather than being sort of like separated by an hour from each other, they're separated by 15 minutes from each other. So things get really complicated that way. There are other time zones that actually do not even include certain months of the year, that they entirely skip over March and go straight from February to April. And whether it does that skipping depends on which year you're in. So lots and lots of fascinating examples like that if you were to watch this first video. Another thing that you maybe have not heard about before is leap seconds. So it turns out that not every minute is composed of 60 seconds. Some are composed of 59 seconds and some are composed of 61 seconds. And that's due to this idea of leap seconds. Which can really mess up your computer code if you are assuming that every minute has 60 seconds in it. So if that's interesting to you, this second video here talks about that and how it screws up computer code. And then this last one is something about what's called Unix time. And if you recall, so the Lambda server is running on Linux, and Linux is an example of a Unix. Mac OS is also an example of a Unix. And the way that all of these Unix operating systems represent time is that time began on January 1st, 1970. And all your computers internally, they're representing time as the number of seconds that have elapsed since January 1st. And it turns out that if you're using a standard integer with 4 bytes on a computer to represent the number of seconds that have elapsed, then you can, or that will keep working until the year 2038. And in the year 2038, we will have run out of seconds and we won't be able to represent time anymore. And so it's predicted that that's going to cause lots and lots of problems for software implemented all over the world, especially on like embedded devices like let's say software vending machines and credit card scanners and things like that that can't easily be updated. So if you Y2K came and passed, people were panicked about that. Nothing really happened, but that's not, from a computer science perspective, nobody really was actually storing years as just 2 numbers, just because it doesn't make that much sense from a space efficiency point of view. But everybody is doing this thing with seconds. And so when 2038 comes to pass, there's a good chance that there will be a big follow-up from that one. Yeah, so that's just my pitch for watching these videos about time, and that it's much more complicated than you think. Actually, maybe one last thing I'll say about it is that if you use this date time module in Python, anytime you're representing time or working with time, always use date time and it'll handle all of these weird edge cases for you. And so the module has sort of a weird kind of interface to it. Takes a little bit of getting used to, but the reason it's weird is just because time is weird and not because Python is weird. Any questions about time before we get to the actual material for today? Okay, so today, this week, we're gonna have a really fun week, I think, in class. I've been looking forward to this week. I'm excited for it. We're gonna talk about something called Unix shell scripting, and we're going to use this to do a really cool data analysis problem. Your homework this week is going to be to analyze coronavirus tweets, to count how many tweets were sent over the past year, the year 2020, related to coronavirus. And let's see, I'm going to skip talking about this kind of stuff and just go straight to the background for now. And so approximately 500 million tweets are sent every day on Twitter. And of those tweets, about 1% are what we call geotagged. And a geotagged tweet is a tweet that contains somehow location information about the user inside of it. So like the GPS coordinates that the tweet was sent from, or the country or the city that the tweet was sent from, something like that. And when somebody signs up for Twitter, puts it on their phone, you have the option, there's just a checkbox that says you want to include this information or not in your tweets. And so this information is included for all the people who check that checkbox. On the Lambda server, I have all of the tweets that have ever been sent with this geolocation information. And if you look in this folder right here, which we will do in a second, actually look at it. This folder contains all of the tweets from 2020, that all of them ever sent that contain this geolocation information. And that's what you're going to be analyzing in this assignment. If you were to count all these tweets, it's about 1.1 billion tweets. And if you were to calculate the total amount of disk space that this data set uses, using this command right here, I'll go ahead and run this command over here. We'll see that it uses a little less than 700 gigabytes of data. So in your assignment this week, you will be having to analyze 700 gigabytes of data. And so obviously that's going to require some careful programming on your part in order to make sure that you do this correctly. One of the things that you cannot do, for example, is just load this entire data set up into memory, because even though the Lambda server is relatively powerful, it does not have 700 gigabytes of RAM on it that you can just load it into. It only has 256 gigabytes. So you'll have to be a little bit careful with how you manage your memory access and things like that in order to ensure that you can actually complete this. And because this data set is so big, we'll have to use parallel programming to analyze it. That if we were to just analyze this sort of one tweet at a time, then it would take about a week of just computation for the whole analysis to complete. And so that wouldn't give you enough time to actually complete the assignment. And so we'll use parallel processing. The Lambda server has 80 CPUs on it. You'll be distributing your code out to all 80 of those CPUs. And so the runtime, instead of being a week, will be like a week divided by 80. And it'll hopefully finish in just a couple of hours. Let's see. So that's the big picture idea of the assignment, what we're building up to today. Before we start getting into the techniques of how do we actually do this, sort of working with these large data sets, are there any questions about just Twitter or the data set in general? Okay, then maybe one last thing I'll say about this before we go on to the techniques. There's sort of this parallel processing framework that we're going to be using is called MapReduce to implement this. And there are lots of different sort of tools for implementing MapReduce. You may have heard of Hadoop is a very popular one. Spark is another popular one. These are tools that sort of, well, they help automate a lot of the things that we're going to talk about this week in class. But for this week in class, we're not going to use those tools. You're going to implement all of these sort of building blocks yourself directly in the Unix shell. And so a lot of the things we'll be talking about this week are this Unix shell. It'll be sort of this kind of grab bag of a lot of different topics, and it might not make sense how they all fit together until the very end. It'll come together. We'll see how you can apply them all to complete this assignment. But I wanted to bring up MapReduce right now just because it's a very popular framework for, say, putting on resumes, getting jobs that people see that, oh, wow, you've analyzed a data set with 700 gigabytes of things in it, or a billion tweets. If you can do that, then you can definitely do the stuff that we handle at our company, which is orders of magnitude smaller. So it's a great project to talk about with future employers during interviews or things like that. Okay, oops. So the material for today, we're going to, again, talking about the Unix shell. And the Unix shell is this interface that when you log into the Lambda server with SSH that you're interacting with. And we're going to talk about it in a lot of detail, maybe filling in some gaps that were maybe not super clear to you before. And eventually we'll see how, by mastering this Unix shell, you can make your Python program, pretty much any Python program you write, parallelize it in a fairly trivial, easy to do manner. So the first thing for us to talk about is file permissions. And there's two commands that will be related to file permissions, this ls-l and this chmod command. ls-l is how we check what the permissions are on a file, and chmod is how we change the permissions. So right now, on my terminals over here, I'm in our class folder, week 7, so the current week. I can type ls, we've used this command a bunch, it just lists all the files in the folder. And if I do ls-l, it lists sort of a more verbose form of what's in the folder. And the things that we're particularly interested in right now are this leftmost column over here. These dashes, R's, and W's indicate the permissions on the file. And they specify what everybody on the computer can do to this file. R stands for read, W stands for write, and X stands for execute. So I'll write that out right here. R equals read, W equals write, X equals execute. And read and write are relatively obvious, that whether you can read and write to the file. We'll talk more about execute here in a second. The other thing to know about these permissions is that they're sort of clustered into 3 groups. You have this leftmost group, which is called the user permissions. Then this middle group right here, which is called the group permissions. And this last group right over here, which is called the everybody permissions, or the all permissions. I'll explain what those are here in a second, but before I do, I want to just highlight that there's a reference right here that you can click on, and it will sort of cover all of this material in detail, and it has a couple good pictures that help illustrate this as well. So I'm going to switch over here to see the first of those pictures. Oops, there we go, right here. And so here it is, highlighting that leftmost part of the ls-l command. And again, it's grouped into 3 components: the user, the group, and the others, or the all or the everybody permissions. And here, because in this set of user permissions, it says R and W, that means the user who owns this file has read and write permissions to this file. I know the user that owns this file because the user that owns it is listed in this column right here. The very first column that contains sort of actual interesting text. This is the user that owns the file. My current user account, you can always get that by typing who am I in the terminal. It's called user test. And so because I created these files right here, I'm the owner, I have permission to read and write. This second column right here is called the group of the files. And the group has these permissions also to read and write. By default, on any Linux system, and the Lambda server in particular, when you create a file, it has the owner as the group name, and the owner as the username, and the same thing as well as the group name. But this could be different, and that would let me specify a small subgroup of people that has extra permissions different than everybody else's. This last set of permissions is what applies to everybody. And so here we can see that everybody has read permissions, but not write permissions. So anybody, all of you on your accounts could log in on your accounts, come to this folder under my account and read these files because it has read permissions for everybody. But if you tried to write to these files, you would not be able to. This is going to be important for the Twitter assignment because these Twitter files are things that everybody has read access to, but not write access to. The particular location right here where these files are located is in this /datafast folder /Twitter space 2020. And if we did that, you can see there's a bunch of zip files in here, one zip file for each day of the year. And if I did ls-l, again, that -l can come at any point in the command, either beginning or the end. We can see the permissions for all of these files. And we can see that they are owned by the user account imazbiki, so my other user account on this machine. And the user and group, both the same. Both of them can read and write to these files. And everybody can read from this file, but not everybody can write from this file. Because my current user account, who am I, is user test. If I were to try to modify these files, I will get a permission denied error. So let's try to modify this file by, for example, deleting it. So rm is the command for remove in the shell. And I'm going to remove the geotwitter 20-01-01.zip file and hit enter. And it'll first give me this error message asking me if I really want to remove a write protected file. It's because I don't have permissions. And I say yes. And then it says it cannot remove it. Permission denied. So there's no worry that you might accidentally do something that will break the assignment for anybody else just because you don't have permissions on the server to be able to do that. So that's the first important thing about permissions, is how to understand who has read and write access to a particular file. The next thing to talk about permissions is this third position over here called execute, and how we can change permissions of a file. In order to do this, I'm going to create a new file. I'll create a Python file and I'll call it test.py. So actually in the top, we'll do vim test.py like this. And let's just add a simple print statement. Hello world up here, and down here, ls-l, we can now see there's this test.py created by default with these same permissions as before. But what I want to do is I actually want to run this file. So we've seen before the simple way of running it, Python 3, test.py like this. But now we're going to see a new way for running these files. And this execute permission gives us a new, simpler way for running files. What I'm going to do is do chmod. So again, chmod is how we adjust the permissions on a file. And then the next part of the command is how we are changing these permissions. So I'll start with an example of group. We'll do group -r. So we're going to look at this test.py file. Recall that these three spots right here for the group. And so G stands for group. And then I want to subtract the read permission for the group on test.py like this. Now, if I do ls-l, you can see that the read has been taken away. It's no longer an R, it's a dash. And so that means people in the group cannot read it. In this case, the group and the user are the same thing. So the fact that my user still has an R here means that I can still read from this file. So I could still say do vim.test.py. I get this sort of vim conflict message because I already have it opened up here. If we close that one, :q, close this one, reload it, everything works fine. But now what I'll do is I'll take away user read permissions, u-r for test.py, ls-l. Now, the user and the group no longer have read permissions. Let's open it up. And you can see that I'm getting this permission denied error down here. So if you ever get this permission denied error while you're opening something up in Vim, it's because you don't have read permission to the file. Because I'm the owner of this file, I can give myself read permission back. Only the owner of a file is allowed to run the chmod command on a file. And in order to give myself read permission back, I use the plus command. So U at the very beginning corresponds to these user section over here, and then plus R test.py adds the R back over here. What I'm going to do next is this execute part. Chmod user plus x test.py ls-l test.py, or let's just do ls-l by itself. And you can see that this x now appears over here, whereas it used to be a dash. You'll also notice that my test.py, it used to be in black, colored in black, but now it's colored in green. And this is just a sort of a hint that the ls command is giving you that you have execute permissions on this file. And so if I were to run just ls by itself, I know that I have execute permissions on this file because it's in green. What execute permissions on a file do is they let us have a simpler interface for running this file. Instead of saying, so python3 test.py, recall that the hashtag like this is a comment in the shell. So I'm going to run it and then have a comment. This is allowed as long as you have the read permissions, and that will run it. But now we're going to see a new syntax of just saying /test.py like this, and this will let me run the file directly without specifically saying what program is actually going to run it. So run it like that. In this case, you'll get a syntax error like this, and that's because I'm missing something in my Python file up here. I'm missing what's called the shebang on the file. You may have seen before a lot of Python files beginning with a line that looks something like this. This line is called the shebang. It's called the shebang because the hashtag is where the sh comes from, and the exclamation point is often pronounced bang, so shebang, shebang for this right here. And this tells the computer exactly which program should be used to run this file. So shebang /user/bin/python3. And now if I do that, it actually runs hello world. This /user/bin/python3 is just sort of a long form of Python3 by itself. And I could down here /user/bin/python3 and then test.py, that would also run it as well. Any questions about any of the permissions or execute information that we've talked about so far?
So do you need execute for the ./test.py?
Yes, exactly. Great question. So the fact that I'm doing this when I'm doing ./test.py, this is what requires the execute permissions. Let's go ahead and take off. So user -x test.py ls-l. I no longer have execute permissions here. There's no X right here. And now if I were to do ./test.py like this, I would get a permission denied error.
Mike, I have a question about the group. I'm a little confused at what it means. Like, how would you alter it in this case? Because your Lambda shiver is a local copy, if I understand it correctly, and as well as for all of us.
Let's see. Yeah, so the group one is a little bit confusing. If you type groups, it will show you all of the groups that you're a part of. And so everybody is a part of a group that has the same name as your username, but you are all also a part of this students group. And there's also a group on the Lambda server for just research that's separate from the students group. And if, say, I wanted to give you all permissions to a file that I did not want to give the research people permissions to, then I could make that file part of the students group and adjust the permissions that way. If the group aspect is a little bit confusing, that's okay. We're not going to interact with it at all in this course. It's just that's what's sitting in between here. The really important things, though, are this user and this sort of everybody permissions. Oh, that's a good question. Are there any other questions so far? Okay, so far we've seen how to use this execute syntax, but we haven't really seen like what's the advantage of it. That, okay, here, yeah, I mean, maybe this is a little bit shorter to type than Python 3 test.py, but kind of who cares? They're really the same thing. The advantage is that we can now use many, many different programming languages sort of interchangeably and give them the same interface for us to use. So I'm going to create another file, and up here, so in Vim, I'm doing :tab-E to open up a new tab in Vim, and I'm going to call this file test.sh. sh is the standard extension for a shell script, just like py is the standard extension for a Python script. And now up here, I'm going to have a different shebang. I'm going to have the shebang for a shell script, /bin/sh. And a shell script is just a sequence of commands, exactly the same as the sort of commands that you might type into your shell down here. So one command that we've seen so far is the echo. This is sort of like the print statement in the shell. And so echo hello world prints out just the string hello world. And so in order to make my test.sh do the same thing as my test.py file, I'll do echo hello world like this. And now I'm going to press GT up here to switch tabs over here. And we can see that now I'm looking at the Python file. It prints hello world. I'll press GT, switching to the shell file. And that's also going to print hello world. Down here, ls-l, neither of these files currently has execute permissions. So I'm going to do chmod all, I'll do user plus x, and test.py and test.sh. In general, for any Unix sort of terminal shell command, you can put multiple files at the end, and it's going to do whatever you say to all of those files. So I'll hit enter with this, ls-l, and now we can see both for test.py and test.sh, they both have this x set right here. And so now I can do /test.py, prints out hello world, /test.sh, prints out hello world. And the way that our computer knew which program should be using to execute these is based on the shebang. It just takes this first, whatever's put in the shebang, and it's equivalent to saying something like /bin/sh test.sh. It'll do the exact same thing. But now we have a convenient method for using all different programming languages with the same exact format.
Mike?
Yep.
I had a question about the shebang. Why do you have the user as before the bin and the test.py, but not in the test.sh?
Yeah, this is a fantastic question. So the question is up here. So I just pressed GT to switch to my Python file. And here I have /user/bin/python3. And I'm pressing GT to switch to my shell file. And here I have just /bin/sh. And the question is, why are those, we call these paths. And the question is, why are those paths different? And the answer is just because this is the location that this program is located on my computer. So let's talk a little bit more about paths and how they work on Linux systems in order to explain this a little bit more. So I'm going to switch real quick over to the notes and show you that this is actually the second thing that we were going to talk about anyways, relative versus absolute paths. So the root of your computer is called slash. And on any Unix system, there's always going to be a path called slash, which we call the root of the computer. And so up here, if I type ls slash, it's going to show me the root of the computer and all the information that's inside of it. I can do cd slash to go to that location and get the same exact information. Your home folders are located in slash home slash your username. That is your home folder. And if you reference your home folder with a slash out in front, we call that an absolute path. And it's an absolute path because no matter where you're located, so currently I'm in the root location. No matter where I'm located, this is always going to tell me it's always going to refer to the exact same place. So yeah, currently I'm in the root location. Let's go into the data folder here and rerun this ls command like this. And you see that that gives me the exact same results. ls by itself, however, gives me totally different results because I'm in a different location. You know it's an absolute path because it starts with a slash, and that means it always refers to the same file. A relative path is a path that does not start with a slash, and that means that it's always going to refer to a different file depending on where you're located on the computer. So if you recall that the pwd command stands for, so pwd equals print working directory, and the working directory is the location that you're currently in. When you do pwd, it's always going to give you an absolute path to the folder that you're currently working in. And if I were to say do something like ls of, so inside here there's a Claremont News data set, ls Claremont News, the way it's going to know exactly which Claremont News data set to work with is that it will take the working directory that you're in and prepend it to Claremont News. So this ls Claremont News is exactly equivalent to saying ls/data/Claremont News, like that. The difference is that this command right here always works the same no matter where you're located because it's an absolute path, starts with a slash. This one is different because it depends on your current working directory. It is relative to your working directory, and so it's a relative path. So how does this connect to these this information up here? Well, both of these are absolute paths in our shebang, and the shebang must always contain an absolute path so that it's always going to be the same no matter where you're running your program from. And again, I know it's an absolute path because it starts with a slash, /bin/sh, and /user/bin/sh. Now the question is, why are these located in these particular folders? And the answer is that /bin, the /bin folder contains sort of like the minimal set of programs needed to have a working computer. And it's a very small number of programs, less than 100, and it's pretty much the same on all systems. You can see that, for example, here's this chmod program. This is a critical part of any computer, the ability to adjust permissions, and so that's why chmod is in this bin system. Another one that we're familiar with is this ls program, critical program for running absolutely any computer, and so that's why it's in /bin. The Python it's a very useful program, but it's not absolutely essential for having a running computer. And so /user is located for any, or what it means semantically is that any programs that you have chosen to install in addition to your base working system go into the /user folder. So that's why Python 3 is in /user/bin, is because it's sort of not strictly necessary, whereas sh is strictly necessary, and so it's in the /bin folder. Any questions so far about paths or absolute versus relative paths?
Yeah, I have one more question about the example you showed a few minutes earlier with the data.
Mm-hmm.
I don't think I fully understand the absolute path. Like, what if you had two folders named data?
Let's see. So let's do an example here. That if we have, so here I have this data fast folder, and we'll go into data. We'll continue using this Claremont News folder. Right now, I'm in the /data folder. So if I were to do ls Claremont News, it refers to the Claremont News that's inside of /data. Up here, I'm going to do :QA inside of Vim. :Q stands for quit, A stands for all, so it'll quit out of both of these windows simultaneously. And up here, ls pwd, notice that I'm in a different folder right now. And so if I run this ls Claremont News, we're going to get this error message saying no such file or directory. I could still, if I wanted to access this Claremont News down here, do ls/data/ Claremont News, and that would let me access the folder in the other location. The reason for having this distinction between the absolute and the relative paths is because now I can make my own Claremont News folder up here, and I can now do ls Claremont News. I just created it, so it's empty. And because my working directory is this, it will refer to the Claremont News that is currently inside of this folder. If I wanted from this location down here to access Claremont News, then I would do ls, take my working directory, and paste it here, then add Claremont News like that. So that's equivalent to just this when my working directory is this. But when my working directory is different, like it is down here, then now it references this full absolute path. The touch command will create an empty file, so I can do touch Claremont News /example ls Claremont News. We can see this example inside of Claremont News. Down here, I rerun this, and now we can see this this example file. Yeah, it definitely takes some getting used to and keeping track of all of these relative versus absolute paths. There's going to be a lot of them in your assignment, and yeah, so it'll just take some practice. And the lab for this week, one of the things that it's designed to do is to give you that practice.
Can I ask one more question, Mike?
Yep, go ahead.
So now you have a Claremont News in week 7 and a Claremont News in the data folder.
Mm-hmm.
What would happen if you tried to access Claremont News with an absolute path, like you put a slash in front of Claremont News? How would it know which one of those to go into?
So there is no /Claremont News folder, because if I were to look in the / folder, if I type ls/, inside of here, there is no Claremont News. And so it only looks directly in whatever's to the left of the file name. Great questions. Any other questions so far? Okay, so we have, let's see, one last thing to talk about with file paths, and that is that on a Unix system, it's possible actually to have any sort of character that you want in your file path, except for a slash. A slash is reserved as a separator between folders, but otherwise you can use whatever weird characters you want. That's different than Windows. Windows has a very strict set of rules about what characters are allowed in file names, but Linux does not. And the way this will come up in your assignments is if we go into this data-fast folder, the data set is located in Twitter 2020. And the key thing about this is that there is a space in the name of this file. In order to access this file, let's see what happens if I do just Twitter space 2020 like this. What it's going to do is it's going to treat these as two separate file names and try to run the ls command on both of these file names separately. In order to get it to treat it as just a single file name, there are 3 possible techniques that you can use. And you'll see me use all of these techniques in lectures from here on out. The first is that if you have a space, you can do what's called escaping the space by putting a backslash in front of it like this. Twitter /space 2020. And if you do that, do this command right here. This backslash tells the computer that the space is not separating 2 separate file names, but actually part of the file name. The next thing that you can do is put them in single quotation marks like this, and that also works. Or you can put them in double quotation marks like this. In the shell, single quotation marks and double quotation marks have a slightly different meaning. In Python, single and double quotation marks are exactly the same. So we'll talk, probably not today, but on Wednesday about what the difference is between single and double quotation marks. But at this point, just know that they both work to combine the spaces into a single file name. Okay, so what we're going to talk about next is a little bit more about these what are called command line parameters. So ls is a command line program. Twitter 2020 is a command line parameter to the ls program. ls is written in some programming language. We don't actually care about what programming language it's written in. Because it has the execute permission bit set, it's going to use to automatically determine which program it should use to run it. And we don't need to say like Python ls or shls, anything like that. It does it for us automatically because it has the execute permission bit set. I'm gonna go back to my home folder now. So cd by itself takes us to our home folder. And now I'm gonna come back up to my week 7 folder up here. So cd proj /cmc046/week 7, and I'm using tab completion again to make that a little bit faster and to help me avoid typos because I'm prone to typos. And what I want to do next is I want to look at our test.py file. So back up here, ls vim test.py, let's open it up. And we're going to create a simple program that looks at command line parameters. In Python, the way you access these is through the sys import. This is built into Python. So no pip install command needed to use this. And then there is a list called sys.argv, which this contains all the command line parameters to your program. So let's comment out that and use sys.argv, and I'm going to do my @p macro in order to print that out just so we can see what the command line parameters are. And now come down here, ls, here's our test.py, I'll do /test.py, and we'll put 1, 2, 3, 4, 5 like this. So this 1, 2, 3, 4, 5 are command line parameters to the test.py program. We'll hit enter, and now you can see that sys.argv is a list, and here's the contents of the list. The very first thing, so entry 0 in the list, is always what was the name of the command that the person actually typed in order to get your program to run. The resulting or the remaining entries in the list are always the whatever the command line parameters are. What I'm going to do next is I'm going to add a whole bunch of spaces over here, something like this, and hit enter. And you can see that we get the exact same command line parameters into our program. This command line right here is interpreted by the shell in order to remove white spaces and get the command line parameters sort of as simple as possible before passing them into your Python program. One of the things it also does is if I put the quotation marks, so I'll put quotation marks around 1 and 2 right here, and then hit enter, you can see that inside of my list down here, my list actually is smaller now, that this 1 and 2 have been combined together into the same entry inside of the list, that they are both equal to argv at, or square brackets, 1. Here's 0, here's 1. And so this quotation mark business is happening on the command line before it gets passed into Python. And that's really important to keep track in your mind about where these sort of differentiations happen. It's very easy to get confused about that. So know that if you have quotation marks in the command line, then it's actually the shell, the terminal, that's handling it before it goes into Python. One of the ways that this comes up is that there is something called the glob in Python, and so, or sorry, the glob in the shell. And so we're going to talk about this glob next, and we'll see how that relates to command line parameters. So here I'm going to type ls. ls by itself, if you give it no command line parameters, lists what are all the files in your current working directory. So, but what if I only want to list some of the files? In particular, if I do ls-l, maybe I don't want to list absolutely everything that's inside of this folder. I only want to list the files that start with test, because I only want to compare, say, test.py versus test.sh. Well, one of the ways that I can do that is actually specifically pass these programs or these file names in like this, and ls-l will look at all of the command line parameters that it's given and only put the output for those particular commands. In this case, I already knew that test.py and test.sh, I already knew what they were, but I can use something called the glob to automate that a little bit more for me. And here, if I do test.star, what's going to happen is that this star will get automatically be replaced by all the files that match the this beginning part. So test.py and test.sh both match this pattern of test.star, where star means anything at all. And so this command right here is exactly equivalent to this command right here. This star, it's a little bit confusing because if you've ever been exposed to regular expressions before, there is a star inside of regular expressions, and it seems like they might be the same thing, but they're actually have totally different meanings. So the glob star is different than a regular expression star. So if you don't know, if you haven't seen regular expressions before, that's okay. We don't need them at all. I just want people who have seen them before, just know, don't be confused. They mean something totally different. So now we need to think about, how does this relate to Python? In Python, we have, well, this star, just like the quotation marks, is something that is handled by the terminal before your program starts. So if I was to write my test.py program, which again is printing out all of the arguments that get passed in. If I do test.py, test.star like this, you might at first think that, okay, here's the name of my program, and here's a single command line parameter, single command line argument to the program. But that's incorrect. If I hit enter, you'll see that this test.star got expanded into test.py and test.sh. It got expanded before it actually got passed into the Python program. This is really important because it's going to make it really easy for us to write programs that are very, very generic. And in particular, for our data analysis program, what we're going to need to do is we're going to need to write a Python program that handles all of the files in the data directory. But there's one file per day in the data directory, and you don't want to have to type out 365 different file names. So the way you do that is you can do test.py, and now we're going to do an absolute path right here, /data-fast, Twitter, \space 2020. If I do that, you'll see that it gets, there's test.py, there is the input right here. Notice that this \space gets, because the space is escaped, it's being passed as a single command line parameter into my program over here. This is all included as a single string, and there is no \/ over here. It's just included as a space. If I did not have this backslash right here, like this, it would be 2 separate command line parameters. So that's the backslash is important. It's also 100% equivalent to having the quotation marks. No difference at all. It means exactly the same thing. Or Python sees exactly the same thing. But now let's see what happens when I put this star right here. The star, again, is going to match all of the files in that folder that match whatever pattern it is that we're looking for. In this case, when we have a star all by itself, that says match everything. There's nothing to restrict the pattern there at all. And so when I hit enter, this list is going to have a huge big thing inside of it, 365 entries, 1 for each file, and there's 1 file per day. If I were to put this whole thing now in single quotation marks like this, you'll see that single quotation marks do not activate the glob. Glob does not work inside of single quotation marks, and so you could have a file that was actually named a star, and in order to access it, you would use single quotation marks, and this would be the name of the file passed in that way. This glob thing is going to be key to having your data analysis code run well for you, so that you don't have to type in all of these file names manually. So if you have questions about them, it'd be good to ask them now. Are there any questions?
Can you put the glob outside of the quotation and will it work?
Great question. So yeah, the quotation marks, like in the shell, you can just sort of like include however much you want inside of the quotation mark. You don't have to include everything like you would in Python. So this also works. That is another thing that is perfectly equivalent to this. Python will see the exact same results. Great question. Any other questions?
Hey, Mike.
Yeah, go ahead, Jonathan.
So I mean, I don't know exactly what the assignment is, but I'm assuming we'll have to do something with all these zip files. So I'm wondering, how do we access the files now that we have this 365 sized list?
Yes, that's a fantastic question. I'd say probably not get to that today, probably Wednesday. But the short answer is in the, if we come up here, look at the code, there's a src folder which has some example source. This map.py has some example code, starter code for you, and this section of code right here actually is what's opening the files. But we'll talk about that in detail on Wednesday. Good question. Yeah, at this point, we're just focusing on the details of the shell so that the discussion of the assignment will go smoothly when we get to it. Any other questions about anything related to the terminal so far, or to the shell? Maybe, yeah, one last shebang related thing that I didn't mention before is that many of you are familiar with R programming. I've taken other classes that use R. If you used this as your shebang, then you could write your code entirely in R, and the computer would know what to do. Okay, so we've talked a little bit about script arguments. The next thing for us to talk about is this idea of redirection. And redirection is one of those concepts that is okay if you don't fully understand it both after today's lecture and really after the course, that I'm going to give you sort of a bunch of examples that complete certain tasks that you'll need to complete. And if you just copy and paste those task examples when you need to do it, then you'll be able to complete the assignment just fine. But redirection is really the fundamental tool which makes Unix shells really, really powerful. And somebody who fully understands redirection is going to just be able to code circles around somebody who doesn't. And so do your best to understand what's going on, but there'll probably be some subtle details that don't fully click. So there's three redirection syntaxes that we need to know, or that we'll be using. This pipe syntax, this vertical bar on an American keyboard, it is just above the enter key if you're pressing shift. On other keyboards, it'll be in different locations. And then the less than and the greater than symbols. I think they're arranged in sort of most useful at the top, least useful at the bottom, but they're easiest to explain the other way. So we'll start explaining this one and then go up to these two. Output redirection is something that we've seen a little bit before in your first lab, that if we have something like echo hello world, by default, echo prints to the screen. And let's rerun our test.py as hello world as well. And it's printing this to the screen. Technically, even though the results are coming to the screen, we say that the output goes to a place called standard out. So output goes to std.out, which is pronounced standard out. So the std stands for standard, out stands for out, and short for output. And what output redirection does is it lets us change the location of standard out. So output redirection changes the location of standard out. The default location for standard out is just to the screen, so you can see them, see the results. But the next most common one is to change standard out to be to a file. So let's say I want to print results of test.py to a file. What I can do is /test.py, hello world, and then use this greater than sign right here, like that. And then the name of the file that I want as the output, and I'll call it example.out. And you can see now that nothing has been printed to the screen down here. And instead, if I look at the contents of example.out, so I'll do vim example.out, I can see here is the contents of what would have been printed to standard out. I guess it was still printed to standard out, but what would have been printed to the screen. When you have really long running pieces of code, that's when this sort of output redirection is the most useful. So in your assignment this week, what's going to happen is you'll have code that will take potentially many hours to run. And you don't want to have to sit there in front of your screen watching it, looking for output to see if it has an error or does not have an error inside of its output. Instead, you use this output redirection to make the output go to a file. And then after the program's done running, you've played Nintendo for a while or done whatever you're going to do, you can come back and just look at the output file to have a permanent record of what it did. The next sort of useful command is input redirection. Input redirection is, instead of the greater than sign, a less than sign. And input redirection says, take a file and use it as the input to a program. So our test.py program right here is not actually using any input yet. So let's create a new file in Python that takes some input. I'm going to open up a new file over here, :tab E, and I'll call it input, just by itself. Notice that I'm not including a .py extension at the end of this file. Extensions don't actually mean anything to Unix systems. They have meaning on Windows systems. Windows uses file extensions instead of shebangs to determine what a file should do. But on Linux systems, we only use a shebang and we don't care about the extensions. So input here, it's not input.py, but it'll still know to run Python because it has that there. And let's do print start with just a simple test like this, come down here, chmod, I'll let everybody execute input, and if I do /input, it executes test like this. I don't think we've seen yet in this class how to actually get input from the keyboard, but it's pretty simple in Python. You just use the input command like that. And we'll say x equals input, and then we will print x down here. Come down here, rerun this command. You can see that it kind of looks like it's hanging right now. Nothing's happening, nothing's printing out. The reason is because as soon as Python hits this input, it's going to wait for the user to type something in on the keyboard, or more formally, wait for something to appear inside of standard in. I'll type example, and example, when I typed it in, got stored in this variable x, and then right here got printed as x. Maybe to make that a little bit more clear, I'll use my @p macro to actually print out x equals, and then x, rerun input, type example, and now you can see it's printing out x equals example. In order to do the input redirection, so by default, when you use input command, input gets input from this place stdin, which is again called standard in or standard input. And by default, standard in is connected to the keyboard to get information from the keyboard. But we can also get input from a file. And if I were to do /input > and then the name of the file, we'll do our example.out. Then example.out contained this text right here. So when we did input, it gathered this text, stored it in the x variable, and now is printing it out. The sort of mnemonic I use to remember which of these less than and greater thans is for input versus which is for output is that you should think of them like arrows. That this is like an arrow shooting example.out into input, and I'll do Control R to find our output redirection example. Here we have an arrow. It's like shooting all of the results of this, shooting it into example.out right there. And you can also combine these together. Let's use input redirection on example.out and put it into example2.out like that. And now we can open up example2.out and see that it contains what was the previous output of the input command.
Hey, Mike.
Yes.
What was the Control R command that you just did?
So anytime you're on the terminal, this also works in Python, you press Control R and it lets you do search through the your history of things that you've typed in. And what I wanted to find a command that contained output redirection. So I just typed a greater than sign and it went back to the first command that contained that greater than sign that I had typed in. If you continue pressing Control R, it will search back through your history for all things that match whatever it is that you've typed in.
Cool, thanks.
Good question. Any other questions so far? Okay. So this is input redirection. This is output redirection. They can be combined together in any combination that you'd like on a particular command. But what's really, really useful is when you not only connect one program to a file, but you connect one program to another program. So let's see, we have the ls command. We've seen that before a lot. Prints out all the information about our inside of our folder. Another really useful command is called the wc command. wc stands for word count, and wc-l will count the number of lines in the input. And so here I've just executed this command. And if I type 1, 2, 3, and then blah, 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 and press Control D down here at the end, you can see, it's maybe a little bit hard to see right here, but it's printed out the number 8 because there are 8 lines right here that I typed in above. So I could do wc-l with input redirection on my example.out, and we can see that that file contains just a single line inside of it. I could do wc-l on my Python files, test.py, to count how many lines of Python my program contains. But let's say I want to count how many lines or how many files are contained in my folder. I could do something like ls, then output redirection into a temporary file like this, and then wc-l input redirection from that temporary file and get an 11 like this. But this is a little bit awkward because I'm having to create this temporary file, and in this case it's actually changing the results of what I want to do. The more clean way to do this, the better way to do this, is just getting rid of this file directly and directly connecting these programs together. And that's what the pipe does. So ls space pipe space wc-l. This is like combined logic of these two commands into a single command where you don't have to create this intermediate file. And so this is take the output of ls, connect it through the pipe to the input of wc-l. Enter, and we get that same 11 files currently existing in this folder. If I wanted to know how many files there are in the data set that we're going to be working with, well, I can do ls/data/ it's data-fast/Twitter space 2020, and we'll pipe that into wc-l, and we get 366 files in that folder. I guess I'd forgotten that last year was a leap year, so we have even more data to analyze. So this pipe lets us combine these two really simple programs together into a more complicated program that lets us answer sort of interesting questions about our data for us. And we'll see lots of useful examples of this pipe connecting things together here in our next class, and we'll use that to solve this data analysis problem about Twitter. Are there any questions at this point about anything that we've covered?
Yeah, Mike, for input redirection, could that be used for command line parameters, or is that only for like inputs in Python and keyboard stuff?
Fantastic question. So yeah, and this is one of the really confusing things about command line programming, is that there are many different ways to get information from like one location into another. And this question is in particular about sort of like what's the difference between input redirection versus command line parameters. And it's in terms of the like what can you do with them, anything you can accomplish with command line parameters, you can also accomplish with input redirection, and anything you can accomplish with input redirection, you can also accomplish with command line parameters. And so it's a little bit of a stylistic choice about which one you end up using for any particular task. And for some tasks, one of those two options will be like clearly easier than the other. So typically, if you're getting a say loading a large amount of information, like the entire contents of a file, input redirection is going to be the easier thing to do. And if you're loading just a small amount of information, like you need a -l, command line parameters are going to be the thing to do. Maybe, so here we have test.py, it's just test.py. Let's take a look at this. Let's see what happens when we do test.py input redirection example.out right here. Notice that this does not call the input function anywhere inside of it. So the input redirection is actually just going to be totally ignored. And when I hit enter here, you'll notice that this input redirection stuff is not included in the command line parameters at all. That this is, again, one of those things that happens totally outside of Python, outside of your code, and is the same for every program that's being run from the shell. yeah, when we work with the actual the assignment starting on Wednesday, we'll see lots of examples of Python programs that you'll be using in the assignment that use both command line parameters versus input redirection. And that will help give you a sense of like, when's the right one for the right job. That's a great question, great thing to be keeping in mind as we talk about things on Wednesday. Yeah, I guess maybe unsatisfying, but there's been a lot of great questions that I've had to say that we'll have to talk about it later, just because we don't fully yet have all the tools that we need to answer all of these questions. Any other questions yet at this point? Okay. So we just have a few minutes left. I want to real quickly talk about for loops in the shell. I'll just show you what the syntax for that is. So just like Python has for loops, it's a fully fledged programming language. The shell also has for loops, totally fully fledged programming language. So we'll see an example right here, bin/sh. In order to create a variable in the shell, the var equals then contents, something like this. It's important that the equals sign be next to the variable. So this is good syntax right here. Var equals that. That's a bad syntax right here. That'll give us an error message, so you can't do that. And then when you have a variable in the shell, you can do something called variable substitution in order to access the variable. So in order to access it, you put a $sign in front of it, and this accesses this variable. Again, this is something that will be substituted before the parameters actually passed to this echo program, and so it'll print out contents. If I do change mod all plus x 4.sh.slash4.sh, print out contents right here, and we don't have to just use the built-in echo. We can keep using our test.py, and we'll get the contents because the substitution happens before the variable, before it gets passed to Python. This is where the difference between single and double quotation marks comes in inside of the shell. If I use single quotation marks like that, single quotation marks capture the $sign as a $sign. If I were to use double quotation marks still allow substitution inside of the quotation. So this is if we had, say, contents, blah, 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 like that, then this will all get passed as a single parameter right here into our arguments. But if I were to leave off these quotation marks, then it's getting passed in as a bunch of different parameters, because all of these are the variable substitution happens, and then they all get treated as separate parameters in test.py. Yeah, we'll pick up talking about variables and then get into the for loops and talk about our actual assignment on Wednesday. But this is a good stopping place for us for today. I have office hours now, so if anybody has questions about things, I'll be sticking around, or questions about anything, feel free to ask. Otherwise,